Welcome to the third video on Fourier series. Alright, so in this video we are going to be looking at Fourier series in several subintervals. When a given function occurs in different intervals, all you need to do is find the Fourier constant at each of these intervals and add them all up together. It gives you the Fourier series. Then from there, of course, you can be able to write your Fourier series. For instance, considering the equation on the board, it says write the Fourier series of a function f of x equals, now you have -1 for minus pi x to 0, and then you have 1 for 0 between x and pi. Okay, so these are two different functions. The first is at -1 and the second is what, at +1, and these are their different what, intervals. So when you have different functions occurring in different intervals, then we are simply saying this is Fourier series identified or defined in what, several subintervals. Now, of course, the first thing to do, let's put down our Fourier series. The Fourier series of a given function f of x, we said is simply a naught all over 2 plus summation from n equal to 1 to infinity of an cos nx plus bn sine nx. Okay, so this is our Fourier series. So all we need to do is to what? Find a naught, find an, find bn, which are the Fourier constants. Now, when it exists between different subintervals, then let's start with a naught. We know that a naught is equal to 1 all over pi integral. Now, if a limit is not given to you, then it's simply from minus pi to pi. But in this case, we are given limits, okay? So this is simply integral for the very first function. First function is what? Okay, let's call it f of x1, okay, which denotes the very first function. Now, the limit is from minus pi to 0. So which means lower limit is minus pi, upper limit is 0. So this is the very first thing to do, times the x plus 1 all over pi integral. Now the second limit is from 0 down to pi. So from 0 to pi, f of x2 times the x, where f of x1 means the very first function and f of x2 is the second function. So whenever you have functions outlined in different subintervals, all you need to do is find the Fourier constant at each of these intervals and add them all up together. So this is the Fourier constant a naught for the first interval, that's for here, and then this is a naught for the second interval from 0 to pi. It's as simple as this. So let's put in the values of the function. So a naught is now equal to 1 all over pi integral from minus pi to 0. We said f of x1, and f of x1 is -1. The very first function there is -1 times the x plus 1 all over pi integral from 0 to pi f of x2. F of x2 is simply 1. So you have 1 times the x, okay? So this is equal to, of course, -1 times the x remains minus the x. So let's factor the minus sign out. We have -1 all over pi integral from minus pi to 0 times the x plus we have 1 all over pi integral from 0 to pi times the x. 1 times the x remains the x. So we have this. Okay, so a naught is equal to -1 all over pi into, if I integrate the x, I will simply have x. Put in your limit from minus pi to 0 plus 1 all over pi. Same thing over here. If I integrate the x, I will simply have x. Put in now your limit from 0 to pi. From 0 to pi. Okay, so at this juncture, we simply effect the limits into the equation. So a naught is equal to upper limit minus lower limit. So wherever you see the value of x, put in upper limit minus lower limit. So I have, for the first case, -1 all over pi into upper limit is 0 minus lower limit is minus pi, okay, plus 1 all over pi into upper limit is pi minus lower limit is 0. We have this. So a naught is equal to minus 1 all over pi into 0 minus minus pi. Minus minus is plus. So this is simply what 0 plus pi, which remains pi, plus 1 all over pi into pi minus 0 remains pi. So if you evaluate this, pi times minus 1 over pi simply gives us minus pi all over pi, plus pi times 1 over pi simply gives us pi all over pi. And of course, this simply implies that a naught is equal to 0. Okay, so the very first Fourier constant a naught is equal to 0. Of course, from here, minus pi over pi is minus 1, plus pi over pi is 1. So minus 1 plus 1, of course, is 0. So a naught is simply equal to 0. You can pen this somewhere. Let's say a naught equals 0. So the value of a naught is 0. Having obtained a naught, the next thing to do is to find an and bn. So let's still start from here. So we find an. An also for the two different functions is defined 1 all over pi integral. Now the very first function f of x1, okay, the limit, remember, is from minus pi to 0. So from minus pi to 0 cos nx times dx. So this is how you find an. So this is for the first interval, plus, considering now the second interval, also 1 all over pi integral. The second interval is from 0 to pi. From 0 to pi, f of x2 also cos nx times dx. You have this. So an is equal to 1 all over pi integral from minus pi to 0. F of x1 remains minus 1. So this is minus 1 times cos nx dx, plus 1 all over pi integral from 0 to pi. F of x2 is 1. So you have 1 times cos nx dx. And an equals 1, of course, minus 1 times cos nx dx remains minus cos nx dx. So factoring the minus sign out, this becomes minus 1 all over pi integral from minus pi to 0. I'm left with cos nx dx, plus, similarly, 1 times cos nx dx remains cos nx dx. This is 1 all over pi integral from 0 to pi cos nx dx. Okay, so an is now equal to, let's now integrate. I have for the first case minus 1 all over pi. If I integrate cos, I've said this in the previous two videos, to integrate a trigonometric function, first thing you do is differentiate the angle, use that derivative to divide the integral of the trig function. The angle of this, or the angle in this trigonometric function, is ns. I have cos nx. Okay, so nx here stands for the angle. If I differentiate nx with respect to x, I'm simply going to have n. If I differentiate nx with respect to x, I will simply have n. Use this derivative to divide the integral of a trig function. If I integrate cos, I'm going to have sine. Then put back your angle nx. It's as simple as this. So which means that integral gives us sine nx all over n, putting your limit from minus pi to 0, plus second case now 1 all over pi into, also integrating cos ns dx, you will still have the same result, sine nx all over n, putting your limit from 0 to pi. So let's effect the limit now and see an is now equal to minus 1 all over pi. Remember, upper limit comes first, minus lower limit. So upper limit, wherever you see x, put in the upper limit minus the lower limit. This is sine nx, and in place of x, upper limit is 0, minus lower limit is minus pi. So I have this times n all over n plus this is 1 all over pi. Same thing here, sine nx. Okay, in place of x it becomes upper limit pi minus lower limit 0 times n all over n. Okay, so an is now equal to minus 1 all over pi into, now this is sine 0 minus minus pi becomes 0 plus pi, which remains pi n all over n. Okay, plus 1 all over pi. Same thing here, pi minus 0 remains pi. This is now sine pi n all over n. Okay, so even without solving further, these two terms are the same. So obviously minus and plus becomes 0. But if you still want to solve further, sine pi, I've always said that in front of a trig function, pi appears as 180 degrees in front of a trig function. So sine pi here simply means sine 180, and sine 180 is 0, which means everything here becomes 0. Same thing, sine pi here also becomes sine 180, and sine 180 is 0, which means everything here becomes 0. So this simply implies that an is equal to 0. So keeping this somewhere, for an is also equal to 0. Now there's a reason why a naught is 0 and an is 0. That is simply the idea behind even and odd function, but we are going to be making a separate video for that in the next video. All right, but let's continue with this solution. So we're done with an. The next thing to find now is bn from the Fourier constants. Okay, so to find bn, I simply say bn is simply equal to 1 all over pi integral. Now for the first limit is from minus pi to 0. So from minus pi to 0, the first function is f of x1 sine nx times the x plus same thing 1 all over pi integral from, now the second limit is from 0 to pi. So from 0 to pi, this is now f of x2 times sine nx the x. So you have that bn is now equal to, not forgetting there is a minus sign here. So for the first case, minus 1 all over pi. Now you want to integrate sine nx dx. This is a trig function sine nx. Okay, we want to integrate this function, and I said to integrate a trigonometric function, first thing to do is to differentiate the angle. The angle in this case is nx. If I differentiate nx with respect to x, I'm going to have n. Use this derivative to divide the integral of the trig function itself. If I integrate sine, I'm going to have minus cos. Pull back your angle nx. So this becomes minus cos nx all over n. That becomes the integral of that function. So this is simply minus cos nx all over n. Put in your limits now from minus pi to 0 plus the second function, which is 1 all over pi, 1 all over pi integral of the same variable sine nx dx, which still gives us minus cos nx all over n. Putting your limit from 0 to pi. All right. So from here, bn is equal to minus times minus becomes plus. I can simply factor n out. This is now 1 all over pi n into cos nx plus, okay, from minus pi to 0 plus, this is 1 over pi n, same thing, factoring n out, and of course this negative sign comes out, so this becomes minus, okay, 1 over pi n into cos nx from 0 to pi. All right, so at this point, let's put in the limits. We have bn is equal to 1 all over pi n So always upper limit comes first. Okay, so I'm taking a different approach now. This is cos nx. In place of x, put in the upper limit. Upper limit is 0. So this is now 0 times n becomes 0. So I have cos 0 minus the lower limit. Cos lower limit is minus pi. So this is cos minus pi multiplied by n. Okay, okay, minus 1 all over pi n into same thing. Upper limit comes first. Upper limit here is pi. So this is cos, in place of x, you have pi n minus lower limit. Lower limit is 0. So you have cos 0. Of course, 0 times n becomes 0. So Bn is equal to 1 all over pi n into cos 0 is 1 minus cos minus pi is actually minus 1. Take note, I've said in front of a trig function, pi appears as 180 degrees. So cos minus pi simply means cos minus 180. That will give us minus 1. Alright, minus 1 all over pi n into cos pi n. Cos pi once again is cos 180, which is simply 1 minus cos 0 is 1 as well. So you have this. Okay, so Bn is equal to 1 all over pi n into 1 minus minus is plus, so this becomes 1 plus 1 minus 1 all over pi into 1 minus 1 here is 0. So this is equal to 1 plus 1 here is 2. 2 times 1 all over pi n gives us 2 all over pi n. And of course, 1 over pi times 0, of course, is off. That is minus 0. So this simply implies that Bn is equal to 2 all over pi n. Alright, so Bn is given as 2. Bn equals 2 all over pi n. So we have this value for Bn. We can now attempt to write our series. So let's write the series of the function. Alright, so since the Fourier series is actually from n equal to 1 down to infinity, it means you can never approach the end. Hence, you can pick a range of value for n, but always from 1. So let's say we are finding the values from 1 to maximum of 3. Alright, so when n is equal to 1, when n equals 1, then Bn is supposed to now be B1 because n is 1. So this is now B1. Remember, A0 is 0, An is 0. So these two terms are out. So we're only working with what? Bn. Now, in place of n is 1. Okay, so this becomes B1. And we said Bn is 2 all over pi n. And n is 1 now. This is now 2 all over pi times 1. So this is equal to 2 all over pi times 1 remains pi. So this simply implies that B1 is 2 all over pi, which is when n is equal to 1. When n is equal to 2, we have to now find B2. And B2, again, this is 2 over pi n. This becomes 2 all over pi. In place of n now is 2. So 2 divided by 2 is 1, which means I'm left with what? 1 all over pi. This simply implies that B2 is actually 1 all over pi when n is equal to 2. Okay, when n is 3, then you have B3 to be equal to same thing, 2 all over pi n. This becomes 2 all over pi. In place of n now, n is 3. So you can simply write this as 2 all over 3 pi. So this simply implies that B3 is actually 2 all over 3 pi. Let's try further. When n is equal to 4, you have B4 is equal to Again, 2 all over pi n. So this is now pi times n is 4. You have this. So this is actually what? 2 all over 4 pi. And of course, 2 goes into 2 is 1. 2 goes into 4 is 2. This is now what? 1 all over 2 pi. So this simply implies that B4 is 1 over 2 pi. So you can continue writing the series as much as you can, then you can stop, since it doesn't have an end. Hence, the Fourier series of that function f of x is equal to, remember, it's supposed to be a naught over 2 and a naught is 0. So you simply have 0 all over 2 plus you have an cos nx, and of course an gave us also 0. So which means 0 times cos ns remains 0. Okay, plus you have now bn sine ns. So we're looking for the sine, or we are writing the sine series. So we start from b1. For b1 we had 2 all over pi. This is 2 all over pi when n is equal to 1. Remember, it is bn sine nx. So this is b1 sine, in place of n now is 1, and 1 times x remains x, plus we considered when n is 2, and we obtain b2 as 1 all over pi. So we have 1 all over pi sine, always multiply by sine. Now nx, n now is 2, it becomes sine 2x, plus again we consider b3 when n is 3, and we have 2 all over 3 pi. So this is simply 2 all over 3 pi sine, now n is 3, so it becomes sine 3x, plus, okay, finally we considered when n is equal to 4, we have 1 all over 2 pi. So this is simply 1 divides 2 pi sine nx. N now is 4, so it becomes sine 4x. So the series continues like that. It doesn't have an end. So in general, the Fourier series of that function, the Fourier series of that function can now be written as f of x is equal to, so since 0 divided by 0 is off, that's 0 plus 0 is off, 0 as well. So we have 2 all over pi sine x, 2 divides pi sine x, plus we have 1 over pi sine 2x, 1 all over pi sine 2x, plus 2 over 3 pi sine 3x, plus 1 all over 2 pi sine 4x, plus dot dot dot, and so on. So the series continues like that. This becomes the final answer to that particular question. All right, so that's the idea behind the Fourier series defined in different subintervals. I will see you in the next video with another question on Fourier series in different subintervals. Thanks and cheers.